Okay, so in last class, we talked about a design process for the spur gear. Now, what I want to do is I want to talk about what type of forces occur on the spur gear. So forces on spur gear. Now for that, let me show you a schematic representation of the spur gear. So this is the spur gear. And I'm going to show you the shaft. This shaft is coming from here. So this is the spur gear. This is shaft. And these are the teeth on the gear profile. Now, if you were to look at the forces on the gear tooth, you would observe that if you have a line of contact somewhere over here, the force transmission is at an angle. So this angle, so usually the force will be transmitted at an angle. This angle is pressure angle. Now, when you have force which is inclined, it will have two components. You are going to have a component in the horizontal direction, and you are going to have a component in the vertical direction. So what I'm going to do is I'm going to specify this as Fn. Ft, the force that is causing this gear to rotate, or the force that is applying torque on this gear, is Fn cosine P. And the vertical force is Fn sine P. Now, in the design process, usually the power is known. Power is known. From there, we find the torque, and then we find Ft, which is the tangential force. So if I want to find out the forces on the gear, I need to find out what are the horizontal and vertical forces on the gear. So I'm going to show you these two forces here. This is going to be Ft, and this is going to be Fr. This is called as the radial force. Now, the resultant of Ft and Fr is actually Fn. Now, why these forces are required? So for this, I want you to think about the gear problem in terms of shaft design. So here is a scenario. The gear is designed, and we want to design the shaft. So shaft design. So gear is completely designed. Now what we want to do is we want to design the shaft. So to design the shaft, I want you to think about this problem. On this shaft, we have torque. On this shaft, we have this torque. But if you look at the locations of the FR and FT, I want to show you the front view. Imagine you're standing here. So you would notice if this is the cantilever support, this is support A, this support A. In the front view, you are going to see FR, and in top, this is the front view. And in the top view, you are going to see FT. So what it means is because of the configuration of the gear and where the forces are applied, we have a shaft design problem where you have bending moment in horizontal direction, bending moment in vertical direction, and torque acting simultaneously. So how do we solve the shaft design problem when I have horizontal bending moment, when I have vertical bending moment, and I have torque? So we looked at the problems like this. Step one is to find out the resultant bending moment, MR. And this MR is going to be square root of BM in the horizontal direction plus BM in the vertical direction. This is the resultant bending moment. And then we have to find out the resultant twisting moment, which is TEQ, which is square root of MR square plus T square. And then once we get the value of torque, we can use the equation T divided by J is equal to Fs divided by R, where J is equal to pi d raised to 4 by 32, and find out the diameter. There are some variations possible in this problem. So the way we have drawn gear over here, it only has one support. That's why this configuration is cantilever beam. But alternate case is going to be, you could have a gear that is supported at both the ends, and you have forces acting at the center span. So in that case, you have to draw the free body diagram. You will notice you are going to have FR, and then you are going to have FT. And then the process remains the same. So I'm going to work out a problem wherein I would like to start from the beginning, design the gear, and then we can proceed to the shaft design. So let me look at a gear problem. Let me try to see a gear problem. wherein we can proceed maybe to shaft design. Sometimes there is one more variation possible. Sometimes we have to design a gear train. Now, gear train means two or more gears that are attached or connected. So if you think about it, say we have a gear. This gear is attached to a pinion. Now this pinion is attached to another gear, and then this gear is attached to another pinion. And then usually you have a gearbox around it. So you have gear 1, you have pinion 1, you have gear 2, and you have pinion 2. Now let's think about what's happening here. Say the gear ratio for the first pair. So gear ratio for G1 P1 say is 3. That means one revolution of gear 1 generates 3 revolutions of pinion. Now, since pinion 1, P1 and G2 are on same shaft, three rotations of pinion 1 would result into 3 rotations of gear 2. And let's take an example. The gear ratio for say G3 P3 is equal to 5, which means one revolution of gear 2, one revolution of gear 2 is going to cause 5 revolutions of pinion 2. So this is G2, this is P2, this is G2 and P2. So which means for 3 revolutions of gear 2, you are going to have 15 revolutions of pinion 2. Now what this means is if you have one revolution of the input, so I'm going to call this input. One revolution of input shaft would result into 15 revolutions of output shaft. Alternatively, one revolution of output shaft would result into 1/15th revolution of the input shaft. For spur gear, power flow can go from point A to B or from point B to A. Now, what is the advantage of this configuration? So the advantage of this configuration is, think about, I want to achieve the gear ratio of 15. So if I want to achieve the gear ratio of 15, that means the radius of the gear has to be 15 times the radius of the pinion. That means if you were to visualize, it's going to be something like this. And we may not have space to accommodate these two because the gear is huge. And with such a huge gear, you could have inertia issues that could lead to balancing issues, size, weight, etc. So in that case, we decide, we actually, as an engineer, we go with a gear train. Especially think about a high-speed transmission. You can't have a very large gear rotating at very high speed because a teeny tiny imbalance would actually cause very high forces, and that would generate very high bearing loads and so on. So we want to be careful when we design the gears. So this is what is the gear train, and you could have maybe multiple of gears attached together. So there could be another gear pair, pinion and gear. And as you can see, the overall gear ratio, is gear ratio 1. So, or I would call RR1 multiplied by RR2. So 3 times 5, the overall reduction ratio is 15. Now, let's work out a problem. Say in this problem, what we are going to do is we are going to design the gear, and then I will show you how to design the shaft for the assembly. So design a gear train, spur gear train. And the design constraint is center distance is equal to 500 millimeters. And this is the geometrical consideration. So basically, you can't have gears apart from each other. The speed of the electric motor. So you have an electric motor. So if you think about it, this is an electric motor. This is the electric motor. And maybe this is a compressor. The speed of the electric motor is 900 RPM. So input RPM, 900. The output or compressor RPM, 200. the torque to be transmitted is 5,000 Newton meter. So they did not give us the power, but in this case, they are saying the torque is 500 Newton meter. And the starting torque is 25% more. Now, usually when you have a gear train and when you start it, the torque required is actually more. And the reason for that is initially everything is at rest. To get that gear train working, you need to overcome the inertia forces. And also you have to overcome the static forces and static frictional forces. Once the things are set in motion, the coefficient of friction drops down, the lubrication is circulated throughout the gear train and other mechanical component, and overall frictional torque drops down. So it's a good assumption to use 25% more torque. And for this, first, determine module and width. Assume 20-degree stub. Second, number of teeth. And PCD. And then the last part is we will do design shafts. The good news here is we are going to assume the gear and the pinion are made up with same material. The first assumption is gear and pinion are made with same material. Now, the torque initial is 1.25 the normal torque. So 1.25 multiplied by 5,000 gives you 6250 Newton meter. The next thing is velocity ratio or reduction ratio is 900 divided by 200, which is 4.5. Now at this point, let's see what is happening here. We have this gear and we have a pinion. So if you think about the center line, this is the center distance. And center distance, they are saying 500 millimeter. So if you think about it, this is the radius of the gear and this is radius of the pinion. So radius of the gear plus radius of the pinion is equal to 500. In other words, diameter of the gear divided by 2 plus diameter of the pinion divided by 2 is equal to 500. And another definition of velocity ratio is nothing but diameter of the gear divided by diameter of the pinion. So now we have two equations. This is equation number 1 and this is equation number 2. So with these two equations, we should be able to solve this problem. So I would say diameter of the gear is equal to 4.5 times diameter of the pinion. So substituting this in second equation, 4.5 diameter of the pinion plus diameter of the pinion is equal to 1000. Solving these two, I get the value for diameter of the pinion as 182 millimeters and diameter of the gear as 820 millimeters. Now with this, we should be able to estimate the velocity factor. We should be able to move on with Lewis's form factor, and then we should be able to find out the module and the width. So once we know this, in the second step, I'm going to find out the pitch line velocity. Which is given by pi dn by 60. BP, I'm gonna use for the gear. So 0.82 times pi times 200 divided by 60, 8.6 meters per second. Now this is needed to determine velocity factor. So for that, we need to go back and see the appropriate equation for the velocity factor. Since velocity is less than equal to 12.5, CV is 3 plus V. That gives me 0.26 as the velocity factor. Now, what I'm going to do is, I'm going to assume, since the pinion and the gear are made up with same material, pinion is weaker. And I need to find out the values of sigma multiplied by YG. So if I were to assume, for this, again, you have to go back to the design data sheet, and I'm going to assume the value of sigma to be 140 Newton per millimeter square. The value for the Lewis's form factor Y is equal to 0.175 minus 0.841 divided by TP. TP is equal to number of on pinion, and that is 0.175 minus 0.841, and here are two variations possible. So I just want to talk about two possible variations. First and foremost, since this is a design problem, as an engineer, you have a choice. What you can say is minimum number of teeth to avoid interference for 20-degree stub should be greater than equal to 14. That comes from the data sheet. So you can assume number of teeth on pinion to be, I'm just guessing, say 18. And what you can do is you can use 18 and find the value of y. And then the design process would continue. Alternatively, you can actually keep y as unknown. So you can say y is equal to 0.175 minus 0.841 divided by diameter of pinion multiplied by module. But as you know, diameter is equal to number of teeth, so DG, number of teeth multiplied by module. So you can use this equation and then keep this as unknown, and we already know what is the diameter, so which means the Lewis form factor will be in terms of module, and then we can find out the module. But either way is totally fine. So assuming you proceed in this fashion and get the value of y. Once you get the value of y, the next thing that you want to do is use the equation WT is equal to sigma multiplied by the face width multiplied by pi times m multiplied by y. So you can actually here use the value of y to get from A, or you can get value of y from B. So what I'm going to do is I'm going to use the value B, but there is no choice in a sense that you can use either or. That's totally fine. So sigma is equal to sigma static multiplied by velocity factor, and that I'm going to assume 140 multiplied by CV is 0.26. This is the value for alloy steel. And then the value is 140, 0.26. Now I need to assume the ratio between B and M. So face width by module. And I'm gonna assume this ratio to be 10. So this is 10 times m multiplied by pi multiplied by m multiplied by y. I'm using equation B, but you can use equation A. And they might give you slightly different answers, but that's okay. So if you look at the diameter of the pinion is 182. Now, a word of caution. With whatever units you use, if you think about it, this is actually a ratio. So whatever is the unit of module has to be the same unit for the diameter. You cannot have diameter in meters and module in millimeters. So whatever you do, it needs to be same and consistent unit. Wt is the tangential force. And this force is nothing but the torque at starting divided by radius of pinion. So if you look at the torque at starting divided by the radius of pinion. Now, here is a little bit tricky part, and I want to pose this question before I solve any further. Can someone tell me what is this starting torque? And for that, I'm going to go back to the gear train. So the starting torque is 5,000. Now this 5,000 torque, is this the starting torque of electric motor, or is this the starting torque of the compressor? So what are we starting? We are starting the compressor. So this 5,000 times 1.25 is nothing but T starting for compressor. Now, what are we designing? We are designing pinion. So the question is, what is the starting torque on pinion? And for that, I need to go back and look at the configuration. Where is my pinion? The pinion is over here. Pinion is rotating at 900 RPM. The big gear or the compressor is rotating at 200 RPM. So can someone tell me what is the starting torque on the pinion? Starting torque on the pinion is 5,000 multiplied by 1.25 divided by the gear ratio. This is the gear ratio or velocity ratio. Now, so what is happening? The amount of torque that is needed to run the compressor is significantly higher. So that's why what we are doing is we are reducing the angular velocity so that the torque can be increased. So as you can see, power is constant. we have T1 omega 1 is equal to T2 omega 2. This is the fundamental equation that we discussed earlier. This is on the compressor. This is on the electric motor. So on compressor, speed is, the compressor speed is low, but torque is higher. On the electric motor, speed is higher, but torque is lower. So by manipulating this torque and speed characteristics, we can achieve the desired power transmission characteristics at the output. So we are going to substitute 5,000 times 1.25 divided by 182 divided by 2. Please note, 5,000 is in Newton meter. So this has to be in meters. So that's why 0.182. And you have to equate equation 1 and equation 2. And as you can see, the only unknown is M. So comparing, you have to use trial and error. Or you can use calculator to find out the module. The module that I got is 10 millimeters. Once we have 10 millimeters, now we can find out the number of teeth on pinion. 182 divided by 10, which is 18.2. So this is not quite right. You cannot have a fraction of a tooth. So you will say 19 number of teeth and gear. We are going to say 19 multiplied by 4.5. And these numbers need to be whole numbers. So you need to round them off. The number of teeth. So fractional. Not possible. And next natural thing to proceed is you want to check the gear for dynamic load. Make sure that the dynamic load is less than the static load. Then you have to look at the wear criteria. Make sure dynamic load is less than the wear load. But let me take the shaft design problem for this gear train. So whenever we are trying to design the shaft, first and foremost thing is, what is the configuration of the gear train? So I want you for a minute to focus on this configuration. So this is the gearbox. So if I were to draw the gearbox, this is how the gearbox looks like. And there are two shafts. So this is shaft 1. This is shaft 2. Ideally, you want to design both the shafts. So, and why do we need to design both the shafts? Because if you think about it, the torque here and torque here. So if this is TP, this is TG. TP and TG are different. However, if you look at Fn, which is the normal force, or if you look at Ft, which is the tangential force, or if you look at Fr, which is the radial force, they are same. Even the pitch line velocity is the same. So if you think about it, since torque on the pinion is less than torque of the gear, since torque on the pinion is less than torque of the gear, the gear shaft is severely loaded. So more loaded compared to pinion. So just to be on the safer side, what we can do is we can design the gear shaft as this is severely loaded. So let's find out. The second assumption is, how is this gear shaft supported? And in this problem, I'm going to assume that this gear shaft is sort of supported in a cantilever fashion. The next thing we need to find out is what is the distance from the bearing support to the center line of the gear. This distance is not given. But this distance is important because if this distance is too short, then it's possible that the housing may interfere with the gear. So we don't want the housing to interfere with gear. But if it is too large, then the bending moment would be significantly higher. The size of the gearbox would be significantly higher. So how do we decide? And for that, one good criteria is looking at the face width of the gear. So if you look at the face width, we assume the face width B is equal to 10 times M. That was the assumption. So this is about 100 millimeters. And what I'm going to do is I'm going to use 1 to 1.5 of B, 1 to 1.5 times B as the distance from the center of the gear to the center of the bearing. So if I were to assume it to be 1.5 times B, and this is the assumption, this distance is 150 millimeter. Now then I need to find out what are the forces. So if you look at the forces, I'm going to show you the side view. This is a side view. We are going to have WT, and we are going to have WR, and here that is going to be WN. So WT, we already know. WT we get from this equation. $5,000 multiplied by 1.25 divided by 182 divided by 2. This is the starting torque. Starting torque divided by the radius of the pinion, but please understand WT, whether you consider on pinion or whether you consider it on gear, is going to be the same. So it doesn't matter. Then next thing is I need to find out WN. WN is WT divided by cosine 20, and WR is equal to WN multiplied by sine 20. In other words, WR is equal to WT divided by tan 20. So once we know WR and WT, we need to find out the moment moment due to WR is equal to WR multiplied by 150 because the beam is cantilever. Moment to WT is equal to WT multiplied by 150. Total M is equal to square root of so you will get the value of the resultant once you plug in the numbers in the calculator. Then you know the value of torque. Now here a word of caution. So this is the torque on gear. So what you need to do is you need to find out the value of torque on the gear, and torque on the gear is 5,000 times 1.25 divided by 1.25. So you need to find out the torque on the gear. And I'm going to call this T. T equivalent is equal to square root of M resultant T square. That gives you the value of torque, and that has to be equated to the equation TEQ J is equal to Fs divided by R, where Fs, we can use the same shaft. This is the torsional stress, this is nothing but tau, and that can be assumed to be 60 Newton per millimeter square. J is equal to pi d raised to 4 by 32. R is equal to d by 2. Substitute everything in this equation, and only unknown is the value of tan. And that is how you would solve the torsion problem. So, any questions on this problem? So I just want to caution you about few things. Always remember, make sure you are using correct torque value for shaft design. You can choose to design shafts. So you can design say gear shaft and pinion shaft, or design max loaded shaft. The next thing which is that comes in design problem is a design of gearbox. So question is our housing design. So how do we design the housing, or how do we decide the dimensions of the case or dimension of the housing? Most of the times they are based on the geometric consideration. So what I want to show you is, think about it like this. So you have designed the gear, and now first and foremost you want to sketch the gear. You have designed the shaft. So next thing is you want to draw the shafts. So you have shaft here. So you have shaft here. Then when we designed the housing, we decided where the bearings would be located. So I'm going to assume that the center line of the bearing is here, center line of the bearing is here. Now, before I proceed and talk about construction of housing, I just want to make sure that everyone understood that based on whatever calculations we did, we can come up with this rough sketch. Any question here? The next thing is, I need some sort of support for the bearing. So let me draw the bearings here. So one bearing here, one bearing here. And you have choice of bearing. You can use a ball bearing, or you can use a sleeve bearing. For this example, let's consider that we have just a bearing. And this is a shaft that is going out of the bearing. This is the shaft that is going out of the bearing. Now I want housing to enclose the bearing. So first I'm going to create a rough sketch. So I want housing, and I will show you the construction of housing. I want housing to enclose the bearing. And then I need some space so that the bearing can be located inside the housing. So this is how it's gonna go. Then I need to construct the outside of the housing. And this shape is up to you. So for example, if someone says, no, I don't like this, I want like more round, then no problem, you can have it round like this. But the key here is you need housing to support the bearing. And we are not done. So, and then finish the other side. Now you can't just have bearing sitting on here, because think about it, you have a shaft, you have a bearing, so you need some sort of a seal. So you're going to have a seal here, and you're gonna have a seal here. Why do we need, and I will show you sort of, and then you are gonna have bolts. I'm gonna show you the slightly larger view. So say you have the top gear or top pinion. This is the center line of the pinion. This is the shaft of the pinion. And then say this is the bearing. So the housing should seat. So let me show you in a different color. So housing should seat the bearing. There is a reason this particular shape is needed, because that way the bearing is supported on one side. Then you're gonna have some sort of a seal here. And I'm showing an exaggerated view. This is the seal. And on top of it, they're gonna have a cover. And this cover will be bolted. So bolts. And the reason for that is usually this gearbox will be filled with lubrication. So lubricant oil. This is oil. And as these gears are rotating, this oil would get splashed everywhere. You want this bearing to be lubricated by oil. So you want this bearing to be lubricated by oil, but you don't want oil to come out from the shaft side. So oil should not come out from here. That's why you have a seal, and then you have a casing that holds the seal together. And that is how the gearbox is designed. But one important consideration here is, and let me pose this question. How to select lubricant oil, and can housing dissipate heat? So Spur gear is quite efficient. So Spur gear efficiency can go above 90%. But nevertheless, what that means is there is going to be a loss. So power loss is equal to 1 minus efficiency multiplied by P transmitted. So for example, if the power to be transmitted is 10 kilowatts and your gear drive is 90% efficient, so 90% efficient, which means 0.1% of the power is being lost in heat. So Q is equal to 0.1 times 10 kilowatts. Now, what happens to this heat? This lubrication that actually takes the heat by means of convection, and that heat gets dispersed. And when this lubricant oil comes in contact with housing warms up and it starts radiating heat, or it can start heat by convection. So what's going to happen here is you are going to have heat loss, which is 0.1 multiplied by 10 kilowatts. So what we want to do is we want to find out the surface area of the housing, and then Q dissipated is equal to the dissipation of the H or the convection constant multiplied by the surface area multiplied by delta T. This is the surface area of housing, and H is the convective heat transfer coefficient, and depending upon whether it's a free convection or whether it is forced convection. What it means is sometimes you might have seen that on this shaft there is a fan. They just attach a fan onto the shaft, and the reason this is very common at the end of the electric motor, you would see a fan, and the reason for that is they want to cool the electric motor coils. Same thing, you can either have a fan if the heat dissipation is needed is high, or if you don't have fan, it is just free convection. And this free convection coefficient and forced convection coefficient can be found out from design data book, and we'll work out a problem wherein the convection coefficients are given. And this temperature is something like a design criteria. So you would say the design criteria, I want my delta T to be say 50 degrees. Which means if the ambient temperature is 25 degrees Celsius, I want my oil to be maximum at 75 degrees. So this is the max temperature of oil. And this 75 degrees C is the temperature that I would like to maintain. And how do we decide this temperature? It depends upon where this housing is located. Say, for an example, if this housing is located in a remote place where no humans will come in contact with it, or there is no flammable objects around, then you can let it go to a higher temperature. If this housing is going to come in contact with flammable substances, it's a part of gas pipeline, then you want to make sure the temperature is lower. Once you decide the temperature, then you need to select the oil that maintains the sufficient lubrication at 75 degrees C. So the oil selection, you want to select the oil that maintains or retains lubrication properties. So oil maintains lubrication properties at desired temperature. Say I'm going to say 75 degrees C. And what you need to do is, for every lubricant, there is something called as Zn by P or Zn by P number. So this Zn by P, if you refer to the British notation, they call it Zn by P. If you look at the American notation, they call it Zn by P. This is a dimensionless number that decides the characteristics of oil. And this is the lubrication property of the oil. So all the lubricants typically show this type of profile. There is certain value of speed, certain value of pressure, and certain value of coefficient of viscosity that governs the coefficient of friction. What you want to make sure is for the given temperature range. So our temperature range is 25 degrees to 75 degrees. In this range, the coefficient of friction for this oil at the given speed. So speed n, so the speed is say 200 RPM. So if you think about it, in the gearbox, you have two numbers. One is the 900 RPM for the given gear, and you have 200 RPM. So you have this upper point and lower point. So what you want to do is you want to find out the oil. It could be SAE 50, SAE or 10W40 or 5W20 or maybe 10W30. So you want to select an oil that within these two ranges. So this is the lower range, this is lower, and this is upper. The coefficient of friction is lowest. So you want to select the oil that matches this profile. And then what you would do is you will say that is the oil that is to be used for this gearbox. And these are some of the important criteria. And then there is an entire branch of engineering, which is called a tribology. That studies the friction, wear, and lubrication. So I'm going to stop here for 15 minutes and then we'll be back and we will start the helical gear design. So I'm going to pause recording. Now at this point, I want to ask this general question. What is our comfort level with spur gear design? Do you want me to work out a spur gear problem or can we proceed to a helical gear design? So I'm looking at the chat window. Do you want me to work out a spur gear problem or you feel comfortable solving the spur gear problem? And I just want to let you know that additional problems on spur gear are worked out and the PowerPoint slides are uploaded. If you need some more examples of spur gear, if you need some more examples, example problems, the video lectures are also available. And some of the problems are similar to your homework problems. So please take a look at the resources that are uploaded in Canvas before you actually start working out the homework and the quiz problems. That would help you a lot. So with that, I'm gonna start with the next part of the lesson, which is the helical gear design. Now, yes, Aaron. So do you want me to work out a problem or you feel comfortable reviewing the material and working out. Okay. What about other students? Everyone feeling okay? And please try to work out the homework and the quiz problem. If there are questions, I would be happy to help via in person, or maybe I can work out problems again in next class. But let me just proceed with helical gear design for the time being. So let's look at the difference between the spur gear and the helical gear. So the idea is, if you look at the spur gear, this is the spur gear, and I'm going to show you the helical gear on side. This is the helical gear. So this is spur, this is helical. If you were to look at the way the teeth are cut on the spur gear, the teeth are cut parallel to axis. So if you look at the spur gear, you would see spur gear something like this. Let me try to sketch the spur gear. So you would see spur gear something like this. Something like this. On the other hand, if you look at the helical gear, the teeth are cut at an angle. So spur gear, teeth parallel to axis, and for the helical gear, teeth are at an angle. So if I were to sketch the helical gear, you would notice there is a distinct angle something like this. So teeth cut at angle, and that angle is called as the helix angle. Now, what is the advantage or disadvantage of helical gear? One thing that you can see, that for the same size, the face width of the helical gear is more. So if you look at BH, for the same size, BH is greater than B. So what does it mean? It means helical gear is stronger. So for the same size of spur gear and for the same pitch circle diameter of the helical gear is going to be stronger. And the reason for that is, since the teeth are cut at an angle, it has more face width available to withstand the load. For the helical gear, there are two types of pitches that are defined. So let me show you what I mean by that. So this is sort of the magnified view of the helical gear. This is the shaft, of the helical gear. And there are two types of pitches. There is something called as the normal pitch, and there is something called as the axial pitch. So this is En, which is the normal pitch, and then you have something called as the axial pitch, and I will show you what an axial pitch is. This is the axial pitch. So PC, an axial pitch, Pn is the normal pitch. And the normal pitch, Pn, is given as Pc times cosine of alpha, where alpha is the helix angle. Now, most important thing here in the case of helical gear is the ratio of module to face width. So as we know, M module is the most important parameter in gear design. For spur gear, face width to module ratio could be anywhere between 12.5. But since the face width of the helical gear is significantly larger than the spur gear, typically the face width of the helical gear is anywhere between 20 to 30 times module of the helical gear. So that is something to keep in mind. What it means is you can have a helical gear that is wider compared to the spur gear. And what are the advantages of having a wider gear? If you have a wider gear, typically the amount of power that the gear can transmit is larger. So if you have a spur gear pair and if you have a helical gear pair, for the same size, helical gear pair would be able to transmit more forces. Now, what about manufacturing? If you think about the manufacturing of helical gear is not significantly different than the spur gear. And what I would recommend that in your spare time, you can just go to YouTube and watch the video on gear cutting. So you have a gear cutting machine and you have a tool and you have a blank, and the tool cuts the gear and gradually the blank rotates. So in the case of spur gear design, the tool is parallel to the blank axis. So basically the tool is parallel to blank axis. In the case of helical gear, it is at an angle. So, and that angle is nothing but the helix angle. So typically, you would see helix angle alpha ranging from 20 degrees all the way to 35 degrees. Now, this is great, but then what are the disadvantages of the helical gear? And I want you to think about the forces that are acting on the helical gear and spur gear. So in the last lesson, we talked about the forces on the spur gear. So forces on the spur gear, you would have a radial force. So you will have a radial force. You would have a tangential force. and normal force is the resultant of these two. So Wn is the resultant of Wr and Wt. Now I want you to think about for a minute that on the helical gear, you're going to have a force which is at an angle. So what that means is if you look at the component of this force, you're going to have a component in the axial direction. So in the helical gear, you have the radial force, you have tangential force, and you have axial force. So this is the axial force. Now the question here is this axial force good or bad? The answer to that question is it actually depends, because for an example, in a certain case that if the spur gear and the helical gear are part of the gearbox, you can just use a simple bearing, a ball bearing or a roller bearing, and spur gear would be able to work just fine, because the ball bearing is not supposed to take any axial forces. If you have axial forces, the life of ball bearing gets reduced, and bearing inner race and outer race would separate. In the case of helical gear, you have to use either taper roller bearings. So you have to use the taper roller bearings. So taper roller bearings or thrust bearings. So or you have to use thrust bearing, so that to compensate for that axial thrust. Now in certain cases, you want to have axial thrust. I give you a very simple example. Say for an example, the helical gear is the last gear in the gear train, and this shaft is attached to the springs and then attached to a clutch plate. So there's a clutch plate, so drive plate and driven plate. So this is the clutch. And as we know, for clutch to function, you need to apply some amount of axial load. Otherwise, the clutch will not work. So if you were to use a helical gear, then you don't need additional means to maintain the pressure, because of the axial thrust generated because of the helical gear. The clutch will be self-loaded. So in other words, the clutch will be loaded by this helical gear. And that's why you will see in most of the manual transmissions, the last gear that actually, or the first gear, depending upon how you see it, that is matching on the clutch side is typically a helical gear, because the helical gear is going to give you a thrust, and that thrust is going to maintain some force on the clutch, and that will be useful for the power transmission. So depending upon what your application is, you want to use the helical gear. Now, so the question is, what if I want to compensate for the thrust given by the helical gear? So here is the problem with the helical gear. So if I have a helical gear, and I'm going to show you a helical gear like this helical gear is going to generate the force in the axial direction. So what I do is I combine this with another helical gear. So, and this helical gear just has opposite helix, and this is called as the double helical gear or the herringbone gear. So this is a double helical gear. So what is the advantage or disadvantage of double helical gear? So as you can see, left part of the helical gear will give you an axial thrust that will be compensated by the right side of the helical gear. So this is called as the double helical gear. And if you have a double helical gear, then you can actually just use a thrust or a simple ball bearing and it should be fine. And if you are going to use a double helical gear, you can go as high as 45 degrees helix angle. Alpha can go all the way to 45 degrees. And that is the important difference between the helical gear and the spur gear. So if given a choice, say if you are asked a question, what gear train would you choose? And at that time, you have to decide, do I need a spur gear pair? Do I need a helical gear pair? How much of space do I have? What should be the width of the gear? How strong the gear should be? Is axial force desired, or if axial force should be minimized? So there are various ways you can see the gears. But usually when you look at the power transmission, you will see the combinations of spur gear and helical gear. Now, what is the difference in terms of the design process for the spur gear and the helical gear? So first and foremost thing is, if you look at the design process, so design of helical gear, of helical gear, it is similar to spur gear. So what that means is we need to find out the Lewis's form factor Y. So Lewis's form factor. For helical gear, we have to find out Lewis's form factor. But if you were to look at the helical gears, see if the number of teeth on the helical gear are, so basically T. So T is equal to number of teeth on helical gear. What we do is we find out something called as TE, which is the equivalent number of teeth on spur gear. So what does that mean? It means what we do is, for calculation purposes, we convert a helical gear into a spur gear. So what we do is we convert a helical gear into spur gear and perform the calculations. So all the tables for spur gear will be used for helical gear design. Except instead of T, we are going to use TE. So what is the relationship between T and TE? TE is the equivalent number of teeth, that is T divided by cosine cube alpha. So once again, alpha is the helix angle. So once you find out the number of teeth on the helical gear, before you do the design, what we need to do is we need to find out the equivalent number of teeth on the spur gear, and then assuming the spur gear design process, we continue with the design. Now, couple of small variations. So first thing is, in the case of helical gear, you are going to have a pressure angle and you are going to have a helix angle. So pressure angle for helical gear could be between 15 to 25 degrees. The helix angle can go anywhere between 20 to 45 degrees. Addendum is usually 0.8 times mod u. Dedendum is 1 times mod u. Minimum total depth is equal to 1.8 times m. So if you were to add addendum and dedendum, that's what you get. And then the thickness is 1.5 times mod u. Now, if you look at the design procedure is exactly the same. So first step is beam strength design. So beam strength and the equation that we used for spur gear, the exact same equation we would use for beam strength. Wt is equal to sigma naught times the velocity factor multiplied by b multiplied by pi times module multiplied by y prime. And y prime is the Lewis form factor based on, so form factor based on equivalent number of teeth, TE. So Lewis's form factor based on equivalent number of teeth. The next step is what would you take as the velocity factor? And the equation for the velocity factor that we used in the spur gear design, we can use the same values. Then the next thing is what would be the value of sigma naught? Sigma naught is the strength of the material, which comes from the spur gear design table. Or data book. Step number 2 is we have to find out the dynamic load on the helical gear. So next step is find dynamic load. Dynamic load is given as WD is equal to WT plus 21 V, B, which is the face width, multiplied by C, multiplied by cosine square alpha plus WT cosine alpha divided by 21V plus square root of V times C cosine square alpha plus WT. Now, let me point out the difference between the helical gear equation and the Spur gear equation. As you can see, in the Spur gear equation, this cosine alpha and cosine square alpha factor was not in the equation. And the reason for that is for Spur gear, alpha value is equal to 0 for Spur gear. So which means cosine alpha is going to be 1. So it is the same equation. The only thing in the case of helical gear, since alpha is non-zero, we have to take into account the effect of cosine alpha and cosine square alpha. The values of V is the pitch line velocity. Again, factor C we can find out from the table in the Spur gear. And again, WT is the tangential load. The next thing is similar to Spur gear. We need to find out the static tooth load. So static tooth load is WS is equal to sigma E, exact same process as the Spur gear, multiplied by B, multiplied by pi, multiplied by M, multiplied by Y prime. And then the static tooth load, WS, has to be greater than WD. That is the condition that needs to be satisfied for safe gear design. The next part is wear load. For wear load, we have to use the similar equation, and in that case, the equation is WW is equal to dP B Q K divided by cosine square alpha. The difference between the Spur gear equation and the helical gear equation is this factor cosine alpha. And then you can find out the values of Q, values of K based on the table, or if you want to find out the value of K using the equation, you can use the same equation given the Spur gear with small change, which is the surface endurance strength multiplied by sine of phi n divided by 1.4 in the parentheses 1 divided by EP plus 1 divided by EG, where EP is the Young's modulus for the pinion, EG is the Young's modulus for gear, and phi n is the normal pressure angle. Now, last but not least is how do we design the shaft? And design procedure for shaft design procedure. So shaft design. It's similar to Spur gear, but the only difference here is we have to find out three loads. So shaft design. So you're gonna have WT, which is tangential load. Then we are gonna have WN, which is the normal load. Then we are gonna have WR, which is the radial load. And we are gonna have WA, which is the axial load. And let me show you these loads on the helical gear. So this is the front view of the helical gear. And this is the top view of the helical gear. So we have the front view and we have the top view. So you would notice in the top view, I'm gonna have the tangential load, and in the front view, I'm gonna have a radial load. I can show axial load in any of these views. So I'm gonna have an axial load. I'm gonna have a tangential load. And then I'm gonna have a radial load. And assuming the supports same process, you are gonna have torque. So all these forces, out of that, we have to understand that normal load Wn, and this is super important. Normal load is because of the resultant of tangential load, radial load, and axial load. And I just want to contrast this with the spur gear. In spur gear, normal load is square of tangential load plus radial load. This is for the spur gear. For helical gear, normal load is square of tangential load plus radial load plus axial load. And this is a perfect time to show a three-dimensional state in the case of helical gear. So what I'm trying to show is I want to show all the angles in the helical gear. And actually this interpretation is super important. So what I want you to understand is this is the tooth of the helical gear. This is the tooth of the helical gear. And on this helical gear, we have the normal force, and I want you to observe this very, very carefully. This is the normal force that is acting, Wn. Now, if you look at the component of Wn, now I want to show you the component of Wn. This is a component of Wn. And you have another component of Wn, which is over here. This force is the radial force, because as you can see that this is going towards the radius. Now, if you look at the component of Wn in the horizontal plane, and I want you to observe this very, very carefully. This is the tangential load. And this is the axial load. So I will give you a minute to think about the three-dimensional force system. So this is the three-dimensional forces on helical gear. Now, what it means is let's think about in terms of angles. So as you can see, if my helix angle is zero, I want you to see what is going to happen. If my helix angle is zero, then my normal force, so let me show you A, B, C, D, E, F, G, and H. So if my helix angle is zero, my normal force, which is actually going through AG, would go through BG. So what is that helix angle doing? Because of the helix angle, my normal force is going through A and G rather than B and G. So this angle is actually alpha. This is the helix angle. Now, the next angle that is quite important is the angle between the normal force and the tangential force, and that is nothing but the pressure angle. So if you look at the projection here, this is the pressure angle C. So you have helix angle, and to see the helix angle, you need to look from the top. So you need to look from here, and then you will see the helix angle. If you want to see the pressure angle, you will have to see from here. So now what it means is I have this three-dimensional force system, and I have to resolve these forces when I'm going to do the gear design. And to do the gear design, assuming the alpha value is known, assuming the pressure angle value phi is known, step one is we find out the value of Wt. Wt is torque divided by the radius. So this is the tangential. And then what we do is we resolve the tangential force in the direction of alpha, and actually in the direction of alpha and phi, and then we find out the component Wr and Wa. So I will work out a problem, and at that time these force systems will be clear. But before I begin, I want you to visualize that it's the diagonal from A to G. The diagonal in this three-dimensional force system, the diagonal from A to G is actually the force that is causing that gear, helical gear, to rotate. And the reason for that is this is three-dimensional case because you have a helix angle, alpha, and you have a pressure angle. In the case of spur gear, the force system is two-dimensional. So basically all the forces would be in the plane AEHD, so which is the front plane, or would be in B, C, D, and F. So B, C, G, and F. So it could be in the front plane or in the back plane. But for the helical gear system, you have a completely diagonal going from all the way from A all the way to G. And same thing, what we need to do is we need to find out the moment because of WT. We need to find out the moment because of WR. We need to find out the moment because of WA, and then find out the total moment. And then, so you have to find out resultant moment, and then we have to find out T equivalent, which is square root of T square plus mr square, and then use the equation and then find out the value of the diameter. So this is the overall procedure for helical gear design. So let me ask you if there are any questions. There are no questions. I would really like to work out a problem. Any questions? Not, I will go ahead and work out a problem. So in this problem, we are designing a helical gear pair. So design helical gears. The power transmission P is equal to 15 kilowatt. That is the power transmission. The teeth are 20-degree stub. So this is the pressure angle, and the gear are shaved off on the addendum. So this is a stub gear. The next step is the helix angle. Helix angle is 45 degrees. That's quite a helix angle. The pinion runs at, so speed of the pinion is equal to 10,000 RPM. The pinion runs at 10,000 RPM. And the diameter of the pinion is equal to 80 millimeter. So pinion diameter is 80 millimeter. Gear diameter is equal to 320 millimeter. The gear diameter is 320 millimeter. The material is cast steel. So material is cast steel. And allowable static stress sigma is equal to 100 Newton per millimeter square. So allowable static stress is given to us, and we have to find out face width. We have to find out module, and we have to check gear for wear. So we have to design the gear. So step one is based on the information given, we have to find out the torque. So power is equal to 2 pi nt divided by 60. So power is 15 kilowatt, which is equal to 2 times pi multiplied by the speed divided by 60. From here, you can find out the value of torque is 14.3 Newton meter. Now what we want to do is, we want to find out the tangential load on the pinion, WT. So one thing that I want you to remember is tangential load, which is WT, is responsible for torque. Normal force or the radial force or axial force cannot give you torque because they are not perpendicular to radius. Only tangential force is perpendicular to radius. So if you look at WT is equal to torque divided by the radius of pinion, 14.3 divided by the diameter of the pinion, which is 80 millimeters, which is 80 divided by 1000 divided by 2. So with this, I can find out the force, which is 360 newtons. And with that, I should be able to find out the number of teeth on pinion. As we know, the relationship between the diameter is number of teeth multiplied by module. So diameter is D, T is equal to number of teeth multiplied by module. So TP is equal to dP divided by M. dP is 80 M, and please note that I'm assuming module to be in millimeter. The diameter is also in millimeter. Next thing, I need to find out TE, which is the equivalent number of teeth. Equivalent number of teeth is TP divided by cosine cube alpha. So 80 M cosine cube 45 degrees, that gives me 226 divided by M. Now what I need to do is, I need to go back to the Spur gear chapter and find out the Lewis's form factor equation for 20-degree stub. So once I do that, the Lewis's form factor equation is 0.175 minus 0.841 divided by TE. And that equation is 0.175 minus 0.841 divided by TE is 226 divided by M. And this equation comes down to 0.175 minus 0.0037 M. And as we know the diameter, the velocity or the pitch line velocity is given as pi times d n divided by 60, pi 80, 10,000 divided by 60 is equal to finally 42 meters per second. You are going to get answer in millimeters, but I would convert that answer to meters per second. And the reason is this information will tell me what should be the velocity factor equation. So I need to find out the equation for CV, or velocity factor. Since the velocity is very high, which is 42, I am going to use the equation for velocity factor, which is given in the Spur gear chapter, 0.75 divided by 0.75 plus square root of V. So that is 0.75 plus square root of V is 42, and that gives me the answer 0.1. So 0.1 is the answer. And I'm going to assume the face width B. Now here is a design consideration. You can go as low as 12.5 to all the way up to 30 times n. And this is just a design guideline. So pretty much you can assume the relationship between the face width and module to be 12.5, and maybe a little bit discussion here. What dictates the optimal relationship between the module and the B? So finally, what you want is you want your gear to have a certain proportion with respect to the radius. So this is the face width B, and say this is the diameter. So if you look at the diameter of the gear, which is number of teeth multiplied by module, and if you look at B, again, that is some constant. I'm going to call it some constant K multiplied by module. This is so constant. And this is number of teeth. And essentially, what I'm looking for is I'm looking for D by B ratio, which is T divided by K. So sometimes what you have is you have a thick gear. So I will show you what I mean by that. So you can have a gear like this. It could be a spur gear or it could be a helical gear. And you can have the mating gear or meshing gear somewhere over here. Or you can have a gear which is something like this. And there is nothing right or wrong answer in here. But the disadvantage of a gear, something like this, you are going to have a very high unbalanced forces. If the gear has a significantly large face width, it's going to take more space in the axial direction to accommodate in the housing. So this ratio dictates what B to M ratio we should be choosing. And again, if you look at the design data book, there are some empirical relationships. So for example, when you look at the gear design guidelines, that they will tell you that for certain application, you can choose the gear ratio for certain values. You can choose B to M ratio of 12.5 or B to M ratio of 15, B to M ratio of 13, something like that. But B to M ratio of 12.5 is a good start. So the next step, which is using all these equations, is you have WT is equal to sigma O times CV multiplied by B multiplied by pi multiplied by M multiplied by Y prime. And so Y prime is basically modified Lewis's form factor that we just found out. Sigma O value is given to us. Value of sigma V is 0.1. Value of B, I'm assuming it to be 12.5. 12.5 times M pi times M multiplied by 0.175 minus 0.003 times M, and WT is given as 358. So this equation you can solve by trial and error, or you can program this equation in your calculator, and that would give you an answer for M that is approximately 32 millimeters. Oh, sorry. The answer to M is going to be approximately 3 millimeters. And B is equal to 12.5 times 3. Now, the next step is we have to check the gear for wear. So as we know, the velocity ratio is equal to 4. Since it is an external gear, the value of Q is 2 times velocity ratio divided by velocity ratio plus 1 is equal to 2 times 4 divided by 4 plus 1, that gives you 1.6. And this is important. We need the pressure angle, which is the normal pressure angle. And the equation for normal pressure angle is tan phi n is equal to tan phi cosine alpha. This needs a little bit discussion. So phi n is the normal pressure angle. Phi is the pressure angle. And alpha is the helix angle. And what I want to do is, I want to explain these three different angles with the same force diagram that we talked about. So this is WN. And if you think about the helix angle is nothing but this angle alpha. And if you want to find out the pressure angle is basically this. And the normal pressure angle is this. So now you can look at the math, and you will notice that if you were to take, let's think about it. If you take tan of Vn, then you get this vertical line, and then that vertical line is nothing but we need to get a projection. So once you find out the value of Vn, tan phi is 20 degrees, cosine of 45 degrees, and find out value of Vn at 14.4. And once we find out this value, we can find out the EP is equal to EG is equal to 200 Newton per millimeter square. Load stress factor K is equal to sigma ES square sine Pn divided by 1.4 multiplied by 1 divided by EP plus 1 divided by EG. So with this, you're gonna get answer 0.678 Newton per millimeter square. And from that, we should be able to find out the value of WW, which is dP B Q K divided by cosine square alpha is equal to 80 multiplied by 32 multiplied by 1.6 multiplied by 0.678 divided by cosine square 45. And WW is 5554 Newton, and this is greater than WD. So with this, we should be able to make a statement that the design is safe. So this is the helical gear design, and unfortunately I had to stop here, but I will work out one more problem in next class. So I'm gonna stop here, and we will continue with helical gear design and move on to bevel gear and worm gear design in next class.